Homework 15, Sampling Distributions in the Central Limit Theorem, Video 1. In the previous series of videos, we learned what a normal distribution was, a bell curve. A standard normal distribution, a bell curve with a mean of 0 and a standard deviation of 1. And we looked at how to use the z-table to calculate probabilities. Recall that in a z-table, it tells you the area to the left of a z-value, which corresponds to the probability of z being less than something. There were also interpretations of areas to the right and areas in between. We'll review those as we go through this section. So if we're going to talk about sampling distributions, I suppose it's a good idea to start by asking, what is a sampling distribution? Well, you may recall the word distribution from previous videos, where a distribution was just a table that listed all the possible values of something and the probability of them occurring. For example, if we were to draw a card from a deck of cards, and the question was, what suit is it? Then in the left column of the distribution, it would say hearts, clubs, spades, and diamonds. And in the right column, it would list the probability of those occurring, all of them being 25%. So what's a sampling distribution? Well, let me kind of set it up and then we'll take a look at a specific example. And in the next video, I'll show you that things aren't nearly as chaotic as they may seem. Let's consider a population of numbers. In the next series of videos, we'll consider a population of qualitative values, things that aren't numbers. Well, let's consider a population of numbers with a mean mu and a standard deviation of sigma. And now we're going to pick a sample size. It'll generically be called n, but within a given problem, it will always be given to you. For example, n equals 12, or n equals 30, or something like that. Every time we pick a sample of size n, it has a mean. That mean would be called x bar, since it's a sample mean. And we can do that for every possible sample that we pick. So what's the sampling distribution of x bar? Let me underline this in red, because that's really the main idea of this video. What's the sampling distribution of x bar? Well, it's just a distribution that lists all the possible values of x bar and the probability that they're going to occur. Just like a regular distribution. The trick for creating it, though, or rather the problem for creating it, is in order to create it, we have to know every possible sample mean, which means we need to know every possible sample. So what I'm about to show you is more behind the scenes what's going on, and it's not something I'm actually going to ask you to replicate, but it will help you understand the concept of a sampling distribution a little easier. For example, we're going to consider a very, very, very small population that has 5 numbers in it. 1, 1, 2, 3, 4. Now you'll notice that I wrote the second one in red. You'll see why I did that in a moment. And we're going to pick a sample size of 3. So how are we going to make a sampling distribution for x bar? Well, we're going to need to know 2 things. What are all the values of the sample mean we can get? And what's the probability that our sample mean is going to equal that value? So we need to list every sample of size 3. Now the reason I wrote the red one in red is to distinguish it from the other one. So for example, if we were to pick the black one, the 2 and the 3, that would be different than picking the red one, the 2 and the 3. If both of the ones were black, it might be easy to forget, did we pick it or not? So let's pick every possible sample. Now, how can we pick all the samples of size 3, and how many are there? Well, the answer to the second question is 10, if you just take my word for it. So if we're going to choose every sample of size 3, let's just pick them methodically. For example, let's pick the first 3 values. The black one, the red one, and the 2. In fact, let's pick all the samples that have both of the 1s in them. So it can be both of the 1s and the 2, or it can be both of the 1s and the 3, or it can be both of the 1s and the 4. Okay, so now we've got all of them that have both 1s. Now let's pick pick the sample that has none of the ones. That's just 2, 3, and 4. So these are all the possible samples that either contain both ones or none of the ones. So all the remaining samples can only have a single 1. Let's pick all the samples that have just the black one. So the black 1, the 2, and the 3, or the black 1, the 2, and the 4, or the black 1, the 3, and the 4. Those are all samples of size 3 that have the black one but not the red one. And now let's pick all the samples of size 3 that have the red one but not the black one. It's actually pretty easy. We just have to write these again but use the red one. 1, 1, 1, all in red. And again, normally the numbers are not in different colors. This was just to distinguish the 2 different ones from each other, because those ones might have been the same answer given by 2 different people. For example, if we asked 5 people, how many siblings do you have? 2 different people might have said 1, and so both of their answers had to be up there. This should be all 10 of them. It is. Alright, so now that we have every possible sample of size 3, we can calculate every possible value of x bar when the sample size is 3. Remember, that's how a sampling distribution starts. We need every possible value of this random variable. And we are treating this like a random variable because its value depends upon randomly selecting a sample of size 3. So how do we calculate the x bars? Just find the average of each sample. Since each sample contains 3 numbers, we'll just find the sum and divide by 3. So for example, the first sample sum is 4. 4 divided by 3 is 1.3 repeating. And if you hear a lot of noise outside, it's because I'm in the room right across from the construction on the Fine Arts building. So hopefully it won't be too much of a distraction. But let's get back to it. This sample's mean is 1.3, 4 divided by 3. For the second sample, the sum is 5, and 5 divided by 3 is 1.6 repeating. Now in the homework, they would tell you to round off to so many decimal places, but this will do. In the third sample, the sum is 6, and 6 divided by 3 is 2. In the fourth sample, the sum is 9, 9 divided by 3 is 3. In the fifth sample, the sum is 6, 6 divided by 3 is 2. In the seventh sample, 1, 2, 3, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. I'm sorry, we're on the sixth sample. In the sixth sample, the sum is 7. There's a tongue twister for you. In the sixth sample, sum is 7. 7 divided by 3 is 2.3 repeating. In the seventh sample, the sum is 8. 8 divided by 3 is 2.6 repeating. In the eighth sample, the sum is 6. 6 divided by 3 is 2. And remember, we're dividing by 3 because we're finding the sample mean, the sum divided by the number of values. In the ninth sample, the sum is 7. 7 divided by 3 is 2.3 repeating. And in the final sample, the 10th sample, the sum is 8. 8 divided by 3 is 2.6 repeating. All right, so we found every sample of size 3, and we found all of those samples' sample means. Now we can construct the distribution for x bar, the sampling distribution. The first thing we have to do is list every possible value of x bar, and we'll list it from least to greatest. Looks like the lowest possible value of x bar is right here. So 1.3 repeating is one possible sample mean. What's the next highest one? 1.6, excuse me, next lowest. 1.6, and that's the only one. Actually, as we're writing these down, we should be calculating their probabilities. Out of these 10 values, one of them is 1.3 repeating. So the probability is going to be 0.1. And the same thing for 1.6 repeating, only 1 out of the 10 is 0.1. The next lowest value is 2, and I believe there's 3 of them. Yep. So x bar can equal 2, and the probability it's going to be 2 is 3 out of 10, or 0.3. The next lowest value is 2.3 repeating, which shows up twice. So 2.3 repeating shows up 2 out of 10 times, so its probability is 0.2. And then 2.6 shows up twice, so the probability of getting a sample mean of 2.6 is 2 out of 10, or 0.2. And the only other one left is 3. And out of the 10 X bars, only one of them is 3. So this is what's called a sampling distribution for X bar. It lists every possible sample mean you can get from this population if you pick a sample of size 3, and the probability that you would get that X bar if you picked a random sample. In the next video, we'll talk about whether or not this is normally distributed, and if it is, what does that mean, and how can we capitalize on it.